This problem. Yeah. All right, then I think we get started. So it's our pleasure to have Yuhsin Tsai, listeners from Notre Dame. He got his PhD from Foreground and he did his postdocs at UC Davis and Maryland. Now he's a faculty member at Notre Dame. Today he's going to tell us about gravitational waves.
Yep. Thank you very much. Thank you for having me here. It's very nice. I already got a lot of very useful discussions with people in this very wonderful group. So in this talk, I want to discuss something about the anisotropy of the gravitational wave background coming from the primordial fluctuations. So this talk would be based on the few works I did before, and then the last one I'm still trying to write, and hopefully we can put out soon. So throughout the discussion, if there are things that you want to see a more careful calculation or like a more plots, you can either just ask me directly, or I encourage you to also take a look at these works. But the idea is that even though this work just sounds like gravitational wave, and that's indeed what our focus will be, but we'll especially focus more on the anisotropic pattern of the gravitational wave signal. Okay, so what do I mean here? Okay, so I think all of you must have been seeing this very nice picture from Planck. This is how the temperature fluctuation looks like on the CMB background, and then tells us that definitely the universe is not just homogeneous and isotropic. So we do see the energy density fluctuation and also the gravity perturbations in the universe. And we have been learning quite a lot from this anisotropic pattern. So that tells you we really have a physics that we can learn by looking at these fluctuated signals. And we learned some basic things like, first of all, the typical anisotropic temperature fluctuation is of the size of the 10⁻⁵. This is a number I will keep quoting as the primordial energy density fluctuation or the gravity fluctuation. But there's actually one subtlety here I want to explain so that you don't get me wrong. If you literally just look at plot the temperature distribution of this signal, you will get the Gaussian distribution, but the width, it will give you a fluctuation much larger than this value. So 10⁻⁴ to 10⁻⁵, because when people quote, or I will quote the fluctuation to be 10⁻⁵, this is just, you can imagine this is the amplitude for one of the Fourier modes that you are looking at. But when you actually see the signal in position space, you add all the modes on top of each other, the fluctuation will be larger. But throughout the talk, when I was talking about the fluctuation, I'm interested in the amplitude of the fluctuation for the different expansion modes. Okay, so that's why I quoted number.
Is it going to like scale enhancement of like a squaring of L roughly or something like that?
Yeah, there will be the uncertainty.
Right?
That's right. That's right. So in the end is you say L times L+1 times the CL and AN all together, and that will be the fluctuation in the position space. Yeah, that's right. Okay, and then the other thing we have been learning so far is that this temperature fluctuation looks very Gaussian, meaning that they more or less looks like some just random uncorrelated fluctuations. And when you calculate the 2-point correlation function, you do get a non-zero result. So you get a power spectrum. But when you do a higher point correlation function, like a 3-point or 4-point correlation functions, we get a very small value. So the fluctuation looks pretty Gaussian at this point. I'm coming back to the non-Gaussianity later in this talk. Okay. So just from our experience of looking at the photon, we see the CMB fluctuation. We can already kind of expect that if we get to see any of the gravitational wave produced in the early universe from some new physics, phase transition, cosmic string, or just somehow we get a large curvature perturbation from some inflationary model that generates a gravitational wave. If we get to see the signal, they will not show up like a isotropic background, but they will look more like have some anisotropic pattern in it. And this is just, you should take this a cartoon picture just to show the idea. Okay. So just for the motivation to why we are thinking about this, because this is really to say that if we get enough sensitivity and angular resolution to finally see all the signals and see the anisotropic pattern, what we are going to learn is not only about the production mechanism of the gravitational wave, like look at the frequency spectrum of the wave and find out which model fits the data best. There we can kind of learning what's the mechanism that produced this gravitational wave. But at the same time, we also get a picture of the universe, like a deep in the primordial dark age, where all the photon signals or like a baryon signals got washed out by the thermal fluctuations. But gravitational wave is probably the only thing that we can use, trying to get the kind of the CMB map at a much early age. So if we get to see this, we're also learning about the cosmology at the early universe. So following this direction, there are a bunch of questions that we need to discuss, right? So first of all, what's the size of the anisotropic signal that we expect? Is it like 10 orders of magnitude smaller than what we can see in detector, or is actually we do have a chance to see those, at least for some of the more motivated models for producing a gravitational wave. And if we get to see it, what can we learn? It's just we just see the same thing, same perturbation as the CMB, or there's actually a chance that the gravitational wave perturbation can look different from the CMB, and we can learn more new physics there. And finally, probably the most important thing is that given the detector sensitivity that people expect we'll have for future detectors, and also we know there are astral foregrounds, is there really a chance that we get to see the signal? Okay, so that I will also discuss of this a bit. Okay.
Sorry.
Yes.
Just comment on this. You're
yes.
going to talk about B modes.
No, yeah. So these are not the B modes. This would just be the So as I'm going to use the first order phase transition as a source to produce gravitational wave, and this would be the direct production of the gravitational wave. But because of the background energy density fluctuation, curvature fluctuation, we will see the anisotropic pattern. So it's a different from photon passing. Yeah.
Higher frequency than the standard tensor modes from the
Yes. That's right. Yep. But even though here I'm going to use first order phase transition as an example so that I can literally write down some numbers and can study some parametric dependence, we do expect to see the anisotropic pattern for all kinds of signals produced in the early universe. Okay. And if it's not clear to you at this point, don't worry, I will explain this more. So this talk is not about proposing new ideas to generate gravitational wave from a phase transition. There are already lots of works doing this, and it's a very exciting field and has a long history. Just want to let you know that we already have lots of understandings of this mechanism, and even beyond the just simple analytical approximation, people can now do a pretty precise lattice simulations, trying to calculate the gravitational wave production. This the red color stuff here from the bubble collision when the strong phase transition happens. Okay. And then I think the consensus now is that, in fact, in most of the phase transition scenarios that people studied, the dominant energy production from the gravitational production is actually not directly from the bubble wall collision. It's actually from the sound wave that will continually produce gravitational wave even after the bubble collision. But just so that I can, again, write down something, I can discuss the parametric dependence of the signal. I'm going to use the signal from the wall collision using the thin wall approximation to describe the signal. But you can think like the actual signal for the same parameter space that I put for the phase transition can actually be larger than the signal that I'm doing here. Okay. But this will give you an idea. Okay. So I know there are many experts on the first of all the phase transition physics, but just to make sure everyone's on the same page, you can approximate the energy density of the gravitational wave in the following form by comparing to the energy density of the photon today. Okay, this would just be useful to think about some other constraints. So I compare this number to the photon density, and the result is suppressed by this ratio. This rho PT is just the energy density of the particles that got involved in the phase transition, basically, and then divide by the total energy density in the universe at the time, because that determines the Hubble expansion. So there's a suppression factor of the square of that. If not, all the energy density will produce a gravitational wave. And there's also a suppression you will get from the signal from this so-called beta over h factor, which is basically quantifies how strong the phase transition is. So the beta here is basically describe the time duration of the phase transition, because the beta, just as a definition, is just when you expand this bouncing action, the quantifying the tunneling rate, and expand this in terms of the time, and the beta is just the leading order coupling for the time. So the rate will grow as exponential beta times the time to the final time of the phase transition. So if beta is very large, you will have nothing, 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 and at the last moment, everything just phase transition, and then you produce lots of small bubbles. So the signal will be smaller. Question.
So in like first order electroweak phase transition,
yeah,
what would be the sector undergoing phase transition? Like, is that the entire standard model, or is it just like the Higgs?
Oh, you mean the standard model phase transition is not first order? But
like,
are you talking about,
yeah, like I guess.
Oh, right. So there would be like, so for example, maybe your Higgs will carry some terms that is temperature dependent. And then when the temperature drops, your potential keeps changing, and then at some point the tunneling will happen.
Yeah, I'm just asking what counts as being the sector undergoing the phase transition.
Oh, sorry. Oh, okay. Yeah. So right. So that would be basically all the energy density of all the particles that will, once the phase transition happens, it will gain mass, basically.
Okay, so like a
Higgs field, that's all other surface daters, Higgs field.
Yeah, but if it's so light, it always looks just like a radiation, then it doesn't really matter. But for all those heavier particles, that does feel the phase transition happens and then changes the behavior. Those are the energy density.
Okay, I guess I'm just wondering, like in that case, is rho PT over rho total, that is actually a small number, or is it most of the energy density?
I guess you're saying why isn't one standard model?
Yeah.
Why isn't one?
Why isn't it one?
Or is it? Yeah. Because I mean, like all the fermions and stuff participate in the phase transition and that they get mass.
Mm-hmm.
I don't know if that counts.
I think it does.
Yeah.
But there's some difference. Let's talk sector by sector. The Higgs sector, right? So
yeah,
it's a vacuum to vacuum transition. There's energy difference.
for the Higgs sector for sure, right? There's a secondary effect when Higgs occupies some mass, any non-zero density of the particles who actually get mass from Higgs mechanism will change their energy. That's those sectors. But there are other sectors who don't get their mass from Higgs.
Yeah, it just has nothing to do, feels the same before and after the phase transition.
Okay.
Yeah.
So everything but the photons.
Yeah, that's my naive anticipation.
That's also my naive observation, but I'll be happy to go through some, we can check some papers together. But that's a very good question, and then I should have the answer directly, but that's what I think.
Okay.
But yeah.
If I can confess, when I was studying physical energy vacuum, I just counted the latent heat from the Higgs sector alone. I ignored all the rest. So my beta PT and the rho PT is only for Higgs.
It's true that, I mean, other particles like thermals, in principle, they're supposed to give correction.
Yeah, it's also a bit.
Particles, and so this correction may not be small, but it is correction.
Yeah, there's a question I ignore, but I only counted the Higgs sector in my.
Yeah.
So what was the ratio then? It was small.
Yes, small.
It's small ratio.
Can I also ask this?
I should.
It could happen. So in principle, it can be possible that this bubble when it nucleates, it's
Sorry, bubble.
yeah, this true vacuum when it nucleates, it's not spherically symmetric, right? So it could be possible. And if it's anisotropic, from the very beginning, then it would be possible in principle to generate gravitational waves from expansion of a single bubble, right? So,
you mean just directly generate the quadrupole moment just from a single bubble expansion?
Yeah. So
That's,
but
if you have that just expanding, do you get that? Because the center of mass is still the same, right? So you get quadrupole moment. Yeah, maybe if you're not spherically symmetric, can be. Yeah. That's also a good question, but I don't know if people study this possibility.
That's related to the sound wave configuration.
Yeah, but sound wave also depends on the medium, like the wave propagation.
that's a different question.
Yeah.
How it interacts.
I have to say all the simulation I've been seeing so far, I assume that just the
I don't know any
the spherical expansion.
Yeah, I know vaguely remember just one example when this Phaleron, depending on the mass of the Higgs again, and non-realistically the mass of the Higgs, this Phaleron can actually be asymmetric. But I don't know.
Okay. Yeah, it's worth thinking about. Okay, but
so then, sorry,
yeah.
just relating in. So if I compare it to the omega and radiation today,
right?
So the omega and gravitational waves today, is it comparable or much smaller? Omega is the rho divided by rho critical, right? So
right. Oh yeah. Today is
omega radiation is 10 to the minus 5. Right?
So it's small, right?
So omega gravity waves is even smaller.
Yeah, that's right. So you can and you can actually easily satisfy unaffected constraint because you even already from the beginning you can be below 10% of the photon energy. Yeah. So later I will mention a bit about the constraint, but the delta unaffected is always just fine. Yeah. Okay. So let's say even if I can come up some scenario that I have most of the energy density got to participate, but I still have this beta over H suppression that I was talking about. So usually if you do a dimensional analysis, just comparing this rate to the Hubble expansion rate, and then you can estimate what's the size of the beta, and that typically gives you a 10 to minus 4 suppression. But of course, people have lots of ideas for some supercooling phase and have a very strong first order phase transition. So people propose models that you can have that vector as large as like 0.1. Okay, but that would be very, very strong phase transition already. Okay. So as Tony were asking, like in the end, in terms of the average energy density of the gravitational wave from phase transition, roughly that will fall in that window. And then if we have this additional row over row separation, of course, it will go even smaller. But this kind of the more optimistic, or from the NDA estimate to the very strong phase transition regime, the signal will lie around here. So the omega is like 10 to minus 9 or down to 10 to minus 11, kind of comparing to the critical energy density. And throughout this talk, I'll be interested on the phase transition happens between 1 to 1000 TeV range. This just simply because that I'm interested on the physics for the LISA gravitational wave detector, or like the very futuristic detector called the Big Bang observer. And the idea is just putting more LISAs in space. Okay, so if I have time, I will explain a bit why would this help, not only about the sensitivity, but also the angular resolution. And this is just some laser beams and do interferometer in space, basically. So the LISA sensitivity curve is here, and the BDO is around here. Okay. So the idea, the first we learned just from this, and people already know, of course, is that the first order phase transition, the average energy density is indeed way above the proposed sensitivities of these detectors. So if they are there, we will see the signal. But now let's talk about the anisotropy. Okay. So I'm actually a little bit behind for what I plan to. So I'm going to, and I also think most of people already have some feeling about the anisotropy. So I will just select some of the more important message just for this part. So the standard paradigm for the anisotropy of all the signals we see today is from the quantum fluctuation of the infraton. That's the best scenario we have so far. And the idea is that when infraton was rolling on a very flat potential, it both drives inflation, so the perturbation, the space just expand exponentially, and also this infraton will just jiggling when it is slowly rolling. So that will generate the quantum fluctuation will generate the inhomogeneity. But this inhomogeneity will show up as you can look at this by different ways. You can say look at this by because the infraton motion is slightly different. So it changes the relative size of the expansion compared to the physical time. Or you can think about this as after the expansion because the size of the phi wave is slightly different from one patch in the sky to the other. So when they get to oscillate and dump the energy to the visible particles, those energy will be inhomogeneous. And the inflation also makes sure this quantum fluctuation got frozen out when they leave the horizon until at the very late time, the perturbation enters the horizon again. So this is just the basic picture. Okay. 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 So from this, it is not surprised that if I have gravitational wave produced here, I'm going to carry the same. Also going to carry a fluctuation, but because I want to make an even stronger statement for the correlation between the CMB fluctuation and the gravitational wave fluctuation. So that's why let me just emphasize this point a little bit more. So that, let's say that if you want to measure the, let's say, dark matter energy density, okay, of one point in the sky and comparing it to the other, the energy density you are looking at will come from some initial reheating process. You get certain energy density, and I label the different energy density by different color. And then when, let's say, when this energy density got redshift into the lower energy density, then dark matter freeze out can happen. And then from the relative redshift between orange to yellow, this is how the energy density I see for dark matter today, okay? But at the same time, if I have a different location that have a slightly different energy density in the beginning, then the expansion history will look different. So redshift will be different. But it doesn't matter because just sometime later, I'm going to redshift into the same energy density. And from now on, all the physics will be the same, right? Will be identical to the physics here, okay? Because energy density determines the expansion of the universe. So I still have the same relative redshift between the orange to the red so that I can produce dark matter as here. But the only difference is that if now I see the signal at a given physical time, the redshift from the orange to yellow is smaller. So I end up seeing a higher energy density of the dark matter. And this same argument works for every signals we see. I have a gravitational wave production here. I have CMB production here. Just from this point, everything will just evolve with exactly the same history. And the only thing that changes is that I shift a clock up and down just because of the linear perturbation. Okay? So I can totally recover the homogeneous universe just by shifting the clock back. So everything is just described by a single clock in this page. Okay, so this is a very useful way to think about the so-called adiabatic fluctuation, that everything are correlated, and then they got shift back and forth by a single clock. So from this, we can already know that if there's a single clock, meaning that there's a single source of the quantum fluctuation and a single reheating process, then the size of the gravitational wave should basically be the same as the size of the fluctuation of the photon. Okay, and here let me parameterize the delta as the delta energy density over energy density. Okay, so far is okay. And already from here, I can do a very rough estimate of the size of the signal of the size of the fluctuated energy density from one point in the sky to the other for gravitational wave. It would be that the size of the perturbation is of order 10 to minus 5. And this combined together with the average energy density that I described before will give us the energy fluctuation to be about 10 to minus 10 to 10 to minus 7 level of the photon energy density. And the peak sensitivity of the LISA is about 10 to minus 7 of the photon energy density. So it is very hard, but it's not totally outside of the consideration, right? Because for a very, very strong gravitational wave signal, I do have a tiny bit of chance to be able to see things in LISA. And later, I'm going to give you a more careful study by solving the Fisher matrix. Yeah.
In terms of the detectability, you also need to take into account the angular resolution.
Yes, I will talk about that. Yes, very good. So this is just the sensitivity. So at least the signal will be above the noise. Yeah. Okay, so this is the average signal. This will be the anisotropic signal. Okay. So now a little bit of the angular resolution. So again, borrowing the picture we have from studying the CMB. Usually we plot the power spectrum of the temperature fluctuation on this temperature correlation spectrum. We plot it as a function of the L mode. And L mode is just L of the Legendre transform. So basically the higher L, we're just saying that you are looking at fluctuation with a smaller structure in the sky, so smaller hot and cold spot. For the lower L mode, you are looking at the bigger chunk of the fluctuation in the sky. Okay. And for the CMB, we see that for the perturbation mode that enters the horizon, so particles are closely related, before the recombination happened, we'll have this baryon-Coucy oscillation peaks. But after that, the baryon-Coucy oscillation already stops, so they basically just have a pretty scale invariant perturbation. Okay, but it's not totally flat because there will also be the late so-called late Sachs-Wolf effect, which is that when universe expand differently because of the CC started to dominant, and that tilts the spectrum a little bit. Okay. But one thing is that roughly the perturbation is like it's basically scale invariant. Okay. And one subtlety here, which would be useful for us, is that when I say this is a constant actually for the 2-point function of the delta rho over rho I mentioned before, times the L times L plus 1 mode. And turns out this combination is the one will produce the scale invariant perturbation. Okay. So for the LISA angle resolution, they can basically only look at the L modes up to L equals just for the angle resolution itself without thinking about the sensitivity. And for the BBO, the hope is they can measure things to 100. Okay. So this will mean that when we see a signal in LISA, we are actually on this region here. So the region that the CMB also is not distorted by the Parametric oscillation. Okay. So really in this region, when I see the signal, the CMB and the gravitational wave will basically be the same. Okay. And also because of the suppression I was trying to mention, like if you're trying to look for a smaller angular size, signal fraction is small angular size, you get the additional suppression. You can also think of this as you cut the total energy into smaller pieces. Okay. So that given that the strongest phase transition already saturates the sensitivity of the LISA, we actually don't get afford to see even higher L modes in the LISA detector. We only roughly see this part of sky is different from that part of sky, but we won't be able to see a higher resolution modes.
Sorry, so
yes.
if you have small L, then that means that you're kind of affected by the cosmic.
Yes, so we also won't be able to do a good measurement, but at least we know it's a non-homogeneous. Yeah, because if that you cannot just fake, right? Yeah.
And of course, with another complication is that the CMB, at least not in polarization, but in temperature, is like the main signal in the sky. But this primordial signal of gravitational waves is not necessarily going to be a signal that could be unresolved binaries.
Right. So I will talk about the foreground. Yeah, I will talk about foreground definitely. So actually, I do want to spend more time foreground. So let me. I should move on this faster. And I think this part, I mean, you know what I'm trying to say is just that if we get to turn on the BBO because the peak sensitivity is much better, and then we get to see the signal even with the dimensional analysis size of the gravitational wave up to the L of 100 modes. So there we can really see the pattern. But also because of the single clock picture, and also together with the CMB mode with the low L mode, does not have much Parametric oscillation, the hot and cold spot we see in the sky will really be totally correlated from one to the others. Okay, so that's the signal we expect to see. But then the question is that all? Is that if we see the signal, I mean, it's always true, like we should just see the same thing as the CMB, okay? So the interesting thing is that depending on the inflationary and the reheating history in the early universe, we can actually have the gravitational wave to have uncorrelated perturbation to the photon, to the single clock adiabatic perturbation. Because you can easily imagine that during inflation, maybe infraton is not the only field. There can be other field who are doing its own quantum fluctuation, and later just decay, reheat into the universe, either into the dark sector or into the visible sector. It doesn't matter, but that's going to generate a different perturbation. So it's called the curvature model. So as long as so this is again the kind of showing the idea, kind of a rough sketch of the idea. For the energy density, if the infraton, as long as the infraton still generate the dominant the energy density, and then later reheat into the stellar model particles. I don't have time to explain why we call these things with this name, but in the end, it can reheat into the photon, and that's a CMB photon we see. You can also have this other field having a different oscillation that first decay into a sector that produce gravitational wave and later merge with the photon that we see today. So gravitational wave will carry the perturbation only from the sigma, and the photon perturbation will carry a energy density with both sigma and phi, and it can be diluted by the phi with a smaller perturbation. Okay. So in this case, we can indeed generate a different size of the fluctuation in the gravitational wave than the CMB. But then you will say that, oh, does that mean I can generate as large as possible the perturbation I want? And so that I can get a large signal of an isotropy. And the answer is no, because you also have the constraints on how large the energy density perturbation of the gravitational wave can be, because that will still change the gravitational background and then change the CMB photon perturbation. Okay. So there is an isocurvature, the so-called isocurvature constraint on having the additional energy density have a very different fluctuation. And when we were writing the first paper, we saw that, oh, we can just check some tables on some existing literature on the constraint on the additional, you can say, dark radiation perturbation. But turns out there was no such study. I don't know why. So that's why later, with also with Shobhit Kumar, and then my postdoc Subhadri Ghosh was excellent and know these cosmological studies. We just used the Planck data to set up the dark radiation isocurvature constraint, and we can get some bound. And this just to say, in the future, if you are working on some dark sector model that you have dark radiation, have a different perturbation, you want to know what the bound is, please check out this result. Okay. Okay. So the idea is that if I have another quantum fluctuation, I can have a different clock. So I can have a different perturbation that I cannot just simply rescale it back by rescaling one clock. So I can have a pattern of the gravitational wave perturbation to look differently from the CMB photon perturbation. But not even that, there's even a possibility, or at least is allowed, that I can have a large non-Gaussianity in the gravitational wave background that is not in the CMB background or is well within the constraint. Okay, and that would be the case if this field that I say was doing the quantum fluctuation, if there is some non-trivial 3-point functions between this three field, the three quantum fluctuation will now be correlated. So once they reheat into the energy density of the gravitational wave, there will be a 3-point correlation function. Okay. So it's easy to generate this. But then the question is that we already have constraints, pretty strong constraints on the non-Gaussianity. Is this scenario even allowed, or it just shouldn't be there? Okay. So usually when we quantify the non-Gaussianity, what we do is that we take the CMB map, do a Fourier transform into the K space, and we draw a triangle into the K space, not really in the position space, in the K space. And then we just pick, look at the density of temperature perturbation of the three different K values, and then see if there's a spatial correlation or not. Okay. If there's a non-zero correlation, then that's the non-Gaussianity that people talk about. We usually compare the result to the 2-point correlation function with this normalization. So in the end, the size of the non-Gaussianity is this 1 over size of the photon perturbation. So this is a factor roughly 10 to the 4. There's some order 1 factor in front. And then times the size of non-Gaussianity. So you can think this is from 0% all the way to 100%, just the label of the non-Gaussianity. The CMB already sets a pretty good constraint because the typical size of the FCMB, if I have 100% non-Gaussianity, would be 10 to the 4th in this normalization. But CMB already set the bounds and saying it needs to be smaller than 40, roughly. Okay, so you can only have percent label non-Gaussianity. But the hope is a future constraint can get down this to the order 1, so you get a 0.1% or 0.11%. Okay. For the gravitational wave case, if you are in a single clock case, that would mean the non-Gaussianity of the gravitational wave will be the same as the CMB because they are totally correlated to each other. In that case, the size of gravitational wave will be around this 40 saturated current bond, and mass can be like this. But there is a cosmic variance uncertainty on top of this and tells us that this is the best that we can measure things for the maximum L mode that we can use to calculate the bound. As I've told you, for the LISA, the L max is only around order 10. So the uncertainty will be of order 1,000 in this unit. But the size we are looking at from the photon constraint is 40. So in a single sector case, there's no way we can see this. There's just no way, okay? But again, if you have a multiple clock, different reheating, you can do that. And the reason for this, I'm going to skip the calculation. The reason for this is that if you calculate non-Gaussianity carefully, thinking about the 2 different sectors, in that case, you can have a large non-Gaussianity in the gravitational wave, but the imprint to the CMB would be suppressed by the energy density ratio between the sector that have the phase transition versus the visible sector. So this, if you only have 10% of energy density, you can suppress the number by 1,000, and that helps you to hide large non-Gaussianity in the gravitational wave, even for the future constraint, but you can only pick it up by directly looking at the gravitational wave. So in the end, we just make some plot and show you there's some region of the non-Gaussianity that you can see that is not constrained by the CMB observation. Okay, so any other question about the signal itself? Because now I move on to the answering the question how sensitive the future probe will be. I'll talk about some future metrics.
Is there any way you could get this large, this multi-sector? So if you go back.
Yes. Sorry, you mean the multi-clock.
Sector, right? So this is multi-field.
Exactly. Yeah. If you just have other field that was also oscillating and later decayed.
How many fields could you add? How many clocks? Is there a limit? Could I increase the signal by taking in very long?
Yes, there's actually one thing I didn't say because I worry I don't have enough time, but actually it's an important point, which is as you say, naively, I can say, oh, let me just add a different sector and playing with the energy density and then playing with the size of perturbation and see in the end, I can add them up to have an even bigger signal. And the interesting answer is not, because if I crank up the perturbation of this by a factor of 10, let's say, on top of the adiabatic perturbation. In order to keep the final perturbation, I need to reduce the energy density in this sector by a factor of 10. And remember that the rho over rho square suppression, that's going to suppress my average energy density by a factor of 100. So because of that, the rho square suppression, when I put everything together, I will actually lose. I actually see a smaller anisotropic energy density, even though if we get to see it, it will look more, the hot and cold spot will be more different, but the overall energy density will be smaller. Yeah, so it's actually not easy, not easy. Okay,
Sorry.
Yes.
So you consider possible effects function, and you say beta should be kind of large to see this effect, for instance, by Lisa.
For Lisa.
For instance, the other sources of gravitational wave, like
You mean cosmic string?
for instance.
Yeah. So people actually study that, and then, but I'm still trying to understand some of their result. But there are careful calculations on the CL for the cosmic string. It will be different. The spectrum will look different.
It becomes more.
The result they show is smaller, but I also need to make sure, are they more conservative, or maybe there's a way to make a signal larger. Yeah, that's indeed interesting thing to look at. So I think now that's just the last topic I want to talk about regarding this is probably the most important one, which is that can we really see it, even though I give you a very hand-waving order of magnitude argument. But we can actually do this a bit more precisely, given that people have some estimate of what's the noise level they will have, or what's the size of the astrophysical foreground it would be. So even if in the end it's still an order of magnitude comparison, at least I can include in more factors to see if it's plausible or not. Okay. So important thing is the foreground. Okay. So in the frequency region between the ESA and BBO, the dominant foreground will just be the binary systems, merger systems from the black hole and neutron star. And given that frequency, the signal will mainly come from the stage when the binary system was still doing the in spiral phase. So they will produce a pretty steady frequency. So it's pretty time independent and for a long time. So this allows us or people to do some time integral and to estimate what's the typical size of the fluctuation, and also compare that to the existing constraints from the LIGO, because LIGO is actually doing a stochastic background search, and they put some upper bound. And you can add all these informations together. You can try to estimate what's the average energy density of the foreground from this. But as you can imagine, that must have some uncertainty. Okay. But the uncertainty may not be as large as one may expect. So it's like 10 to minus 12 to 10 to minus 10, because we actually know the cosmology quite well. We know how the galaxy distribution as a perturbation very well, because the lambda CDM model is measured very precisely and is good. So there's a good reason why people estimate the average energy density to be in this level, and also the perturbation to be certain level, just based on the existing cosmology we know. But still, there can be a large uncertainty. So in terms of delta omega, it would be the range from 10 to minus 12 to 10 to minus 15, roughly. So the curve we see here is for the average energy density. And then that times the perturbation and also include the different results from different group. So I think it's roughly less around here. Okay. And there's also a spectrum in the L modes, which you can see is no longer flat. It's actually proportional to the L roughly. And that's because the foreground signal is not produced at the one instant in time. It's an integrated effect for a long period of time, and turns out that changes the spectrum. Okay. So this is a good estimate, but of course, who knows? When we do things, then maybe it can be even larger. Okay. So that's why when we do the study, we consider the foreground to can go even larger. Okay. So the thing I'm going to do is that I'm going to use the uncertainty that this collaborations estimated and do a Fisher matrix analysis. Okay. So I'm going to explain a bit more of that, but in order to do that, I need to at least write down a model that at least makes sense for some of the parameters that we want to either measure or want to allow it to vary. So we write down this model for the astrophysical foreground with certain normalization of the amplitude and with some frequency spectrum, and also that the L spectrum that I mentioned before. So there's a good motivation that we know the spectrum will roughly go as a delta equals 1. And also frequency spectrum, we also know quite well because of that in spiral phase, and we know what's the evolution of the frequency. So the gamma will be of order 4/3. But again, we'll just take this as a motivated benchmark value and trying to see what's the uncertainty that we can, the measurement will be on these quantities. Okay. So for the Fisher analysis, of course, I also need to assume what's the signal that it look like so that I can calculate the precision of measuring the signal. So I also put the overall size of the perturbation, put some frequency spectrum given by the simulation, and then assuming some L dependence. So the beta should be 0 if it's the adiabatic perturbation. Okay. Then I'm going to skip the detail of the Fisher matrix. This is basically just probe that if you are on the multi-dimensional manifold and you are trying to move away from the one of the parameter away, a little bit away in certain direction from the benchmark value, how large would the chi-square value changes when you compare the signal to the background? And that's basically it. And you do this in the multi-dimensional space. So we calculate this. But one thing I want to mention a little bit is that about the noise of this detector. Okay. So this is a plot produced by Lisa working group for the sensitivity of the gravitational wave measurement for different L modes or different patterns that we see in the sky. So what comes into this sensitivity is the noise. So noise basically just laser. How much do we trust about our laser and have some like a background white noise? And also there is a pattern of the antenna, which is for Lisa is just a triangle. Okay. So if I have a signal with a certain Legendre polynomial shape that comes in, I use the triangular shape antenna trying to see the signal. And that projection together will give me how sensitive that I can probe the certain mode. So one interesting thing that you can see if you look at the number more closely is that the best sensitivity is the L equals 0. So that's just a look at homogeneous isotropic mode. And then you roughly do a similar good job for the L equals 2 and L equals 4. But when you start to do things like above L equals 4 for Lisa, the sensitivity just decreases like dramatically. And the reason for this is that for the Lisa detector, you basically have two vector antenna, right? You have this arm and this arm, take the time difference, and then you are trying to measure a pattern in the sky. So you can measure, like you can catch some L equals 1. So like a spin 1 signal, you put together, you get a spin 2 measurement. So you can see gravitational wave. But when you measure the correlation function, you see a spin 2. With these two antenna, you add together, you roughly get L equals 4, like a mode. That's the best that you can measure when you use a two vector kind of like of antenna. So that's why all the higher L modes just becomes bad very quickly. And also because of the symmetry of the detector, for the odd number of the mode, you also do much worse if you do Lisa. And this is just the limit. There's no way you can pass this for Lisa. So that's why people are thinking about how about if we have more detectors. And actually, there's a Chinese kind of a proposal, like it's doing similar thing as Lisa. It's called the Taiji, which is basically just putting additional Lisa in the sky with a slightly different orientation. So in that case, you no longer got limited by this L equals 4 mode, because now you can have a more complicated antenna pattern. And the sensitivity curve will now goes down even for the higher L modes. Okay. And this futuristic Big Bang observer, the BBO, is just really just shoot out more LISAs in the sky. So you can increase the sensitivity both by using a stronger laser and then also gets to go to the higher L modes. So because the antenna pattern is now different. Okay. Okay. So with all of this, the sensitivity curve that including the noise, now I can start to answer the question that for a given signal and the astrophysical foreground, if I can see the cosmological signal or not, and also if I can distinguish the cosmological signal to a foreground or not. Okay, because now when I put them together, all the uncertainty were now correlated with each other. So here I just directly give you the result of seeing the anisotropic pattern. So for if you have the strongest phase transition scenario, like a beta over H is 10, so the suppression is the minimum, that will correspond to this orange curve here. Okay, and this plot shows the uncertainty for measuring a quantity. Sorry, this is too small, but for this plot, the y-axis is the uncertainty for the amplitude of the perturbation, assuming the different size of the foreground. Okay. So of course, if the foreground is larger, the ability of measuring the AC would be less powerful. So if this number is larger than 1, that means uncertainty is larger than 100%, then we won't be able to learn anything. Okay. So in LISA, for the strongest phase transition, and assuming adiabatic perturbation, we have a tiny chance to see maybe there is the existence of the Isotropy. This is slightly smaller than 1, but we won't be able to do much. We also won't be able to measure, to give a good measurement on what's the power, what's the spectrum in the L mode. We must see that something seems to be fluctuated. Okay. But for the astrophysical foreground, in that case, it's not that sensitive to the size of this because the size is not very big. But for the astrophysical, for the astro foreground, if it's around the region that I was telling you, okay, there's indeed some chance that we can also see the astro foreground, and probably not be able to measure the spectral shape. But if we are wrong, if the astro foreground is 10 times larger than what people were claiming, then we actually have a good chance to measure the property of the foreground with LISA. Okay, and I'm pretty sure when LISA put that noise and sensitivity curve, I would guess they are also optimistic in some analysis they do. So this is basically what we should expect, the most that we can do with LISA. Okay. If we do get both the LISA and Taiji that in space, and basically the same technology, we just do it twice, then that helps a lot, because in that case, I do have a much better chance to see the phase transition signal. I still won't be able to measure the spectral shape, but for foreground, I also have a small improvement, not much, that I can measure the foreground. Okay. And definitely if I get the BBO, because just to remind you, if we get to see the signal, we should get to not seeing the anisotropic signal, but seeing the isotropic part, the average part of the signal coming from gravitational wave. There will be a huge signal. We will definitely know. If we see the signal is there, we'll definitely know there's something that looks like a phase transition spectrum. And I'm pretty sure people will try to put in more LISA in the sky. So that would be like a BBO. So once we have that, few more satellites, then of course we can do a much better measurement. And on all these plots, the upper boundary is 100% uncertainty. So up to that point, we do have a chance to do a kind of pretty precise measurement on the spectrum and the spectral shape of the signal. Okay, so this is basically what we can learn at least about the anisotropic signal. Okay, that's all. So just to conclude, so if there is a stochastic gravitational wave background, it must show up with an anisotropic pattern for the single clock or two clock pictures that we have. And there is indeed a small chance we can see the strongest gravitational wave from the strongest phase transition, and adding both Taiji to the LISA together can greatly enhance the sensitivity by a lot because of the property of the antenna now being different. The shape is different. The gravitational wave signal can either be correlated or uncorrelated or even have a large non-Gaussianity. So there are definitely non-trivial physics can be there to waiting to be seen if it's there. Okay, thank you very much.
Any more questions?
So when you talk about BBO being like throwing a bunch of LISAs up in the sky, are you talking about putting a bunch of triangles up, each of which only talks to itself? Like you only have lasers going between the 3 points of the triangle, or?
Right, okay, so the proposal people have, of course, I don't think people are seriously working on this right now, but this is a proposal. They just take all this antenna pattern and see how well they can do. The proposal is that they put 1, 2, and these are 2 triangles on the sky, so in total 4. But these 2 will combine as a kind of this Israel star kind of thing.
Okay, and in the 6-pointed star, are all of them sending lasers to all the other ones?
No. So each of them is just a triangle.
Would it not be beneficial to have more lasers sending?
Not necessary, because you need to make sure everything is stabilized. You need to make sure the correlation between the 2. If it pattern becomes too complicated, there may be some engineering issues. So, but if you can do this in terms of the mapping out the anisotropic pattern, it would basically doing the same thing.
Okay, the extra baselines wouldn't help you.
Yeah, probably the only thing you need is just a correlation between if you know the location between one to the others, then that can basically reproduce the information you want to get, because you know the location of all the others. And then, yeah, but again, this is a proposal. So we actually talked to some of people who are like more trying to push this kind of thing. And they all be very optimistic. I guess if they don't, they won't be working on this. But the thing is that if we get to learn how to put things, we already have the pathfinder for the LISA. So it looks like we can put things on the Lagrange point. And this would more be like putting more of those in the sky. Hopefully it can work. Yeah.
What's the time scale for BBO?
Oh, BBO is unpredictable. I think it really depends on what do we see in LISA. If we turn on LISA, I'm pretty sure in the beginning we'll see a bunch of noise and we don't know. So maybe after a few years, we figure out what's the noise. Oh, for all the curves I'm showing here, I assume LISA running for 3 years. Starting 2035, that's the number, that's the time that some people put, but then we'll see. But I think people are working hard, but yeah, but it takes some time.
So how about Taiji? Like how serious people are? What is the time scale?
I can talk to my Chinese colleagues, but it seems like they have serious money plans. Like every government satellite, things are easy to sell. They have fun.
Yeah.
In the beginning, when they make a proposal, the biggest worry is in China, we don't have enough technology preparation for those things, but they are trying to set up new centers and get people back to China and see amazing.
Do you know the time scale?
I didn't follow, so I just I asked friends I will put it on a slide.
Yeah, but technologically, the challenge is mainly how do you make a very precise laser and then the time measurement, and don't destroy it when you put it into the space. So if that part of the engineering can be overcome, then you just shoot more of those into space. Of course, for BBO, they have different motivation. They want to cover this slightly higher frequency regime. So the size of the detector is a bit different, and they also need a stronger laser power. But I think it's not like some for the next generation technology kind of thing. But of course, there would be engineering difficulties to need to overcome. Yeah. Yes.
What actually sets the frequency range for the gravitational waves? Is it like Hubble at the time of the phase transition or something, or is it?
Oh, you mean for the theory that I put?
Like
No, this I just put this because I'm interested on the LISA and BBO. Just roughly this frequency range, but of course you can think about the even higher temperature. The higher the temperature is, the lower the signal would be because of the redshift.
Okay.
Yeah. And there's not much here, but of course you can just keep going for the pulsar timing, and yeah, people do talk about those.
And where do you like gravitational waves from cosmic strings sit?
Oh yeah, those frequency spectrum would be more flat because they keep producing gravitational wave for a long time. So the spectrum will be very different and it will be broader. Yeah. So basically you can repeat all the calculation estimate I do here just for different signals. Yeah, once you produce signal, you can do a feature analysis, you can get a different result.
So you mentioned that you calculate the bound on the perturbation in the dark radiation,
Right.
and it seems quite surprising. I mean, or exciting that that means the CMB constraint on dark radiation can actually be stronger than what it is if the source of the dark radiation is predicted to be, let's say, delta rho over rho to be
Exactly. Yeah.
And people haven't pointed out this fact before. Because some of
They usually talk about that in the neutrino sector, but it's actually pretty hard to have a neutrino model building to do that because everything thermalized.
Yeah, I'm not thinking about neutrino.
Right. So I was just saying that in terms because they asked me about the literature.
Oh, okay.
And I'm indeed doing a calculation on the size of some dark phase transition, even if you have a tiny energy density budget.
Yeah.
But because the phase transition when bubble collision has some finite statistical effect, that you can get a large perturbation. And then that's one example that you can get a large delta rho. There are also papers that suggesting maybe you can use this to constrain the dark matter freezing process, but there's still something people are still under debate. But it's true, yeah. So if you have a scenario, have a larger perturbation, then the constraint on energy density would be much stronger.
I see. Yeah, I have to feel. I will talk to you about
Yeah, definitely. Yeah.
More questions? If not, then let's bring Yuhsin again.
Thank you.
My father's name is Taiji. They can say that Taiji would have been this.